Word tokenization is an important part of text processing. Every natural language processing text has to normalize the text in some way. We start by segmenting or tokenizing the words off. We often have to normalize the format of each of the words. And as part of this process, we're going to have to break out sentences from the text. So let's start by talking about this kind of word tokenization. How many words are there in a sentence? Here's a sentence. I do mainly business data processing. How many words are in that sentence? It's a complicated question. There's a word like is a word? Or how about the cutoff main of mainly? So we call things like main a fragment. We call things like a filled pause. So for certain applications, we might want to be counting these if we're dealing with speech synthesis or speech recognition or correcting things. What about cat and cats? We talked about the cat and the hat. So we define the term lemma. Two words are the same lemma if they have the same stem, the same part of speech, the roughly the same word sense. So cat and cats are both nouns. They have similar meanings. We say that cat and cats are the same lemma, so they're the same word in that sense. We define the term word form to mean the full inflected surface form. So cat and cats, by that definition of word, are different words. They're different word forms. So we're going to use different definitions depending on our goals. So let's look at an example sentence. They lay back on the San Francisco grass and looked at the stars and so on. And let's ask how many words there are in this sentence. So count for yourself. We can define words in a couple ways. Word types, how many vocabulary elements there are, how many unique words there are, and word tokens, how many instances of that particular type there are in running text. So how many tokens do we have in here? Well, it should be easy to count. 1, 2, 3, 4, 5, and so on. So if we count San and Francisco separately, we end up with 15. If we count San Francisco as one token, we end up with 14. So even the definition of a word depends a little bit on what we're going to do with our spaces. How about types? Count for yourself. Well, there's 13 types, again, depending on how we count. So we have multiple copies, the word the, there's the and the. Again, it depends if we count San Francisco as one word or two. And remember our lemmas, we might decide that they and their, since they are the same lemma, although they're different word forms, we might want to count them as the same type, depending again on our goal. In general, we're going to be referring to the number of tokens, which comes up whenever we're counting things with capital N. And we'll use capital V to mean the vocabulary, the set of different types. And we'll use set notation, so the cardinality of the set V is the size of the vocabulary, although sometimes, for simplification, we'll just use capital V to mean the vocabulary size when it's not ambiguous. So how many words and tokens and types are there in the kind of data sets that we look at in natural language processing? Well, let's look at a couple of these. Data sets of text are called corpora. And here's 3 important corpora. The switchboard corpus of phone conversations has 2.4 million word tokens, and there's 20,000 word types in those 2.4 million words. Shakespeare has just under 1 million word tokens. Shakespeare's quite a small corpus. He wrote 800,000 words in his lifetime. And in that less than 1 million words, he actually used 31,000 distinct words. So he had a very, very broad vocabulary, famously. And if you look at a very huge corpus, the Google Ngrams corpus that has 1 trillion different tokens, a very large number of words, there's 13 million types. So how many words are there in English? Well, if you look at conversation, 20,000 different words. If you look at Shakespeare, 30,000 words. And if you combine the two, probably somewhere, not quite the sum of the two, but some larger number. But you look at the Google Ngrams, we have 13 million words. And of course, some of those are probably URLs and email addresses. But even if you eliminate all those, the number of words in a language is very large. Maybe there's 1 million words of English. And in fact, Church and Gale have suggested that the size of the vocabulary grows greater than with the square root of the number of tokens. So as you get n tokens, the square root of n more vocabulary items. So vocabulary keeps growing and growing, and it's names and other kinds of things that contribute to this growing in vocabulary. We're going to introduce some standard Unix tools that are used for text processing. So I have here a corpus of Shakespeare's complete works. You can see here's the sonnets, and it goes on through all the plays. So let's start by extracting all the words in the corpus. So we're going to do this using the TR program. All right, so the TR program takes character and it maps every instance of that character into another character. And we've specified TR-C, which means complement. So it means take every character that's not one of these characters and turn it into this character. So in this case, it's take every non-alphabetic character and turn it into a carriage return. So we're going to replace all the periods and commas and spaces in Shakespeare with new lines. So we're going to create one line, one word per line in this way. So let's look at that. So we've now turned the sonnets into one word per line. And now we're going to sort those words to let us look at the unique word types. So let's do that. And you can see here's all the A's. There's a lot of them. A occurs a lot in Shakespeare. And this is a very boring way to look through all of Shakespeare. We don't want to do this. So let's instead use the program unique. And the program unique will take that sorted file and tell us for each unique type the count of times that it occurs. So let's try that. So here we have all the words in Shakespeare with a count along the left. This is the product of the unique program. And we can walk through. So we know that in Shakespeare, the word achievement with a capital A occurs once. The word Achilles appears 79 times. The word acquaint 6 times, and so on. So that's interesting, but it would be nice if we didn't have to just look at these words in alphabetical order, but if we could look at them in frequency order. So let's take this same list of words and now resort it by frequency. So now we have the most frequent word in Shakespeare is the word the, followed by the word I, followed by the word and we have the actual counts in Shakespeare. So that here is our lexicon of Shakespeare sorted in frequency order. There's some problems. One is that the word and occurs twice because we didn't map our uppercase words to lowercase words. So let's fix the mapping of case first. So let's try that again. We're going to map all of the uppercase letters to lowercase letters in Shakespeare. And we're going to pipe that to another instance of the TR program, which replaces all of the non-alphabetics with new lines. And now we're going to do our sorting as we did before. We're going to use unique to find all the individual types. Unique-C tells us the actual count. And then we're going to sort again, means numerically, and R means start from the highest one. And then we'll look at those. So let's do that. All right, so now we've solved the problem of the ands. So now we only have lowercase and. We don't have our uppercase and appearing. But we have another problem. We have this D here. Why is the word D or the word S, why are they so frequent in Shakespeare? We also have to decide a standard that we're going to need for our words. So for example, if our input is Finland '(S) capital, how are we going to tokenize Finland depends on our goals. So we might choose to keep all the apostrophes in, and then we have Finland '(S). We might choose to replace all the apostrophes with nothing, or we might choose to eliminate all the apostrophe S's. Similarly, we might choose to expand the whaters to what are, and the ims to I ams, because if we're, for example, looking for all the cases of I for some sentiment analysis task, or if we're looking for all the cases of negation for some task, we might want to turn isn't into is not. How about Hewlett-Packard? We have to decide whether words like Hewlett-Packard are going to be represented or with a space. The same is true with phrases like state of the art. We'll have to decide for words like lowercase, should they have a dash? Should they have no dash at all? Should they have a space? We talked about the issue of San Francisco. And then issues with periods become a huge issue. We have to decide if we're going to represent MPH, leave the periods in, and then all of our algorithms that use periods for splitting things are going to have to be sensitive to this. The issue of tokenization becomes even more complicated in other languages. We have the French phrase l'ensemble, or the L apostrophe to be a separate word, and if so, do we turn it into the full article le, or do we keep it as L apostrophe or just an L by itself? We'd like it to match the same word ensemble, even if a different article occurs before it. So we're going to want to break them up for some reasons, but then we're stuck with these sort of non-words. So another issue we have to deal with. In German, the long nouns are not segmented as they are in English. So a word like life insurance company employee in English would be segmented up. In German, we're going to get into these very long phrase, but spelled as a single word. So for German tasks like information retrieval, we're going to need to do compound splitting. In Chinese and Japanese, we have a different problem. There's no spaces at all between the words. So here's, and we've shown you the original Chinese sentence here. And now here's the sentence segmented out. So here's Sharapova now lives in US and so on. So in English, we segment out. Chinese, we don't. So if we want to do natural language processing on Chinese, any applications, we need to break things up into words. And so we'll need some way of doing that. Similarly, in Japanese, we have the problem that there's no spaces between words, and we have the problem that there are multiple alphabets that are intermingled. There's the katakana alphabet, there's the hiragana alphabet, there are kanji, which are like the Chinese characters, and there's romaji, the Roman letters. Another complicating issue that has to be dealt with in tokenizing Japanese. Word tokenization in Chinese is a common research problem that has to be addressed when doing any kind of Chinese natural language processing. And the characters in Chinese represent a single syllable, often a single morpheme, and the average word is about 2.4 characters long. So a word has to be broken up into approximately 2 or 3 characters. And there are lots of complicated algorithms for this, but there is a standard baseline segmentation algorithm called the max match, the maximum matching algorithm, also called the greedy algorithm. So let's look at max match as an algorithm. We're given a word list of Chinese, so a vocabulary of Chinese, a dictionary, and a string. We'll start a pointer at the beginning of the string. We'll find the longest word in the dictionary that matches the string so far, starting at the pointer. We'll move the pointer over the word in the string, and then we'll go back and move on from the next word. So let's just see an example of that working. I'm going to pick an English example that's easier to think about. We'll take the phrase, imagine English was written like Chinese with no spaces. We'd have a phrase like the cat in the hat all run together. And we have a dictionary that has words like the and cat. So we look at this and we say, what's the longest word in our dictionary that matches the beginning? And the longest word in our dictionary is the, because the is not a word and the is not a word, and so on. So we'll start with the, and now we've gotten to here, and now we say what's the longest word starting with C, and the longest word is cat. So now we say what's the longest word starting with the I, and so on, and we do a good job. How about the phrase the table down there? We take the spaces out of the table down there. What's our segmentation, our max match segmentation algorithm going to do with the table down there? Think a little for yourself. You may think that what it's going to do is produce the table down there, but there's a problem. English has a lot of long words. English has the word theta for the variable, and so instead of the table down there, we're going to get theta, right after that, bled, and then own, and then there. So we're going to get theta, bled, own there. So max match is in fact not a generally good algorithm for this kind of pseudo-English, English without spaces, because English has these very long words and short words all mixed together. But since Chinese in general has relatively consistent word length, this works very well for Chinese. And it turns out that modern probabilistic segmentation algorithms work even better. So that's the end of our section on word tokenization.